All right. So good afternoon, everybody, and thanks for having me at your conference. As my screen says, my talk is going to be on seaweed and using microformulations as a strategy for for the food security. And so, why do we think that seaweeds are a good source of nutrients? So right now, the oceans are being invaded by sargassum species, especially in the Atlantic. And the picture down below here shows the coast of Barbados from an article I took a few days ago. And the coast is covered with brown seaweeds, and that's good because we have lots of raw material for our production. But it's also bad because seaweeds can these brown seaweeds produce toxic hydrogen sulfide gas, and it's not as bad in Mauritius, where I'm from, but Mauritius is very dependent on the seaweed, on the tourist industry, and having the coast in this shape is not great for our industry. So we need to find a way to exploit these seaweeds as well as a way to get rid of it. And why do we think this industry has potential? Brown seaweeds are a significant source of micro and macronutrients, and Mauritius, which is a tiny island located in the Indian Ocean, has a very large exclusive economic zone of over 2 million square kilometers, and it's home to over 400 different algae seaweed species. And unfortunately, up to now, the nutritional profile has not been very well characterized. And one of the problems is that, especially for brown seaweed such as sargassum, it tends to accumulate some heavy metals such as arsenic. And one more thing is that even if we have the seaweed in crude form, we need to extract some nutrients from it. But the extracts such as vitamin C are not very stable. Therefore, one of the things we tried to do was collect seaweeds from different species, like red, green, brown seaweeds from all around the island, and characterize their vitamin and mineral content. So this is a snapshot of a paper that we have submitted for publication, which is currently under review. This shows all the types of water-soluble vitamins that are present in several seaweeds. We analyzed over 50 types of seaweeds. And we also did something similar with the fat-soluble vitamins and different types of minerals, such as silicon, potassium, sodium, etc. So armed with this knowledge, especially knowing that brown seaweeds can be a good source of vitamin C, we went out to collect one seaweed species, Sargassum obovatum, which is present in abundance everywhere on the island, but mostly on the west and south coast. And it's very easy to collect. We just go on the beach and just grab it. So we don't need to dive or anything. And the samples that I'm going to talk about today were collected in March 2022. And at that time, it was at the end of summer, so the temperature was around 28 degrees, kind of warm. And what we did was look at the heavy metal content and the different physical chemical parameters of the water. So the water is clean based on the analysis we did, which was performed independently by a local certified lab. And so it had no heavy metals that we know of. So using that, we tried to look at the water-soluble vitamin content of these seaweeds. So to do that, we use the protocol displayed on the screen here. So we took the crude powder, put it in an extraction solution. So the extraction solution depended on the type of vitamin that we were trying to extract from the seaweed, so vitamin B or vitamin C. And every step shown here is important. So we cannot just sonicate, we cannot just mill it. And at the end, we have a clean seaweed extract that we can send to HPLC analysis to measure the amount of vitamin that's present in there. So we did that, and what was interesting is that the different components of the seaweed, so the leaves or the vesicles, contained different amounts of vitamins. So for example, vitamin C was present in a high amount in vesicles compared to the leaves. But for future applications, we are probably going to use the whole crude extract without separating into different types of sargassum. So that's the amount of vitamin that was present in the seaweeds. And like I said, in this current extracted form, it's not very stable. So especially vitamin C, it has to be stored at 4 degrees. And this slide here shows the experimental conditions we use to do the extraction. So for the vitamin C, we use a different HPLC column compared to vitamin B, and the graphs show the retention times of the different vitamins. So vitamin C, we have a single peak, so we extract a pure vitamin, and for vitamin B, we can analyze all the components of the B complex at the same time. And down here below is again reduce the different amounts of vitamins that we obtained. And using that, since I mentioned that the vitamin extract itself is not very stable, we tried to find a way to stabilize it. And one of the ways we tested was to look at encapsulating it inside the microspheres. And shown here is the method that we use. So as the microsphere capsule, we use another food grade polymer called carrageenan, which with the structure displayed down here. And what you'll see here is that in most of our chemicals are either food grade or natural products. So we use carrageenan, and we use an immersion technique that has carrageenan dissolved in water, and we mix it with sunflower oil at high speed to produce this water and oil emulsion that contains the microspheres. And to encapsulate the vitamins, either pure vitamin C or if you freeze-dried extract, we dissolve that in the carrageenan. And one of the other tests that we did was to see whether a coating of chitosan changed the release kinetics of either the seaweed extract or the vitamin, or stabilize the microspheres further. And we chose chitosan again as it is a sea-based polymer, so it's obtained from, for example, from shrimps or chitin, and it has a positive charge as opposed to carrageenan, which has a negative charge on the surface. So to verify that the chitosan coating was working, we did an FTIR measurement on the 2 different types of microspheres, with and without chitosan. And when you look at the microspheres with chitosan, you see an extra peak that appears at around 1529 wave numbers. This is a characteristic of the primary amines present on the chitosan molecule. So once the microspheres were synthesized, we tried to measure the size of the microspheres, and by varying the vortexing speed of the synthesis, we could tune the microparticle size to different sizes. So for example, mixing at 1000 RPM, we had a particle which was around 64 micrometers. And vortexing at 8000 RPM, we had a particle that was around 17 micrometers. So that way we could also tune the size of the microparticles. And what we also tried to measure was the once we had the microparticles, like I said before, we added either vitamin C or a freeze-dried seaweed extract that we obtained from the protocol I described earlier. And to do that, we took a node and we encapsulated that, and we wanted to know how much exactly was being encapsulated in these spheres. So to do that, we weighed a known mass of microspheres in an amber vial, added 2 ml of the extract solution, and allowed that to dissolve for 1 week at 4 degrees, filtered, and measured the vitamin C concentration using HPLC using the parameters I mentioned before. And using that, we tried to calculate the encapsulation efficiency, given that we knew how much vitamin C we started with and how much we ended with. Unfortunately, what we saw was that we had very low encapsulation efficiency, so that's definitely something we need to work on. But what's interesting here is that for the smaller microparticles, the encapsulation efficiency was nearly 2.5 times higher. So that's one way of modulating the encapsulation, of increasing the encapsulation efficiency. And we also calculated the total amount of vitamin C present per gram of microsphere, and this is also quite low. So in 1 gram of microsphere, we had about 2 milligrams of pure vitamin C. We could increase that to 5 using a higher vortexing speed. And with the seaweed extract, we had 3.6 milligram for the low RPM and 5.04 for the high RPM. So we could, what this demonstrates is that we can encapsulate vitamin C in this setup. We can encapsulate seaweed extract that contains vitamin C, and we just need to work on the efficiency of encapsulation. And what we also need to work on is how exactly the release of vitamin is going on. So I don't have all of the data to show you here, but what we are trying to do is look at the release of vitamin C in simulated gastric fluid and simulated intestinal fluid, which are at different pH. So what we are going to do in this case is take a known mass of the microsphere, dissolve in either one of those two, and study this solution at 37 degrees, and at known time intervals measure the amount of vitamin C content present in the solution. So that gives us an idea of how much vitamin C is being released over time. The preliminary results show that there's no vitamin C being released in the intestinal fluid at the higher pH, but we do see some in the gastric fluid. But all of the data analysis is still in progress. So to conclude, what we did was collect. So we collected sargassum bovatum from the beach and characterized the water-soluble vitamin content, isolated the aqueous vitamin C extract, and then encapsulated that in microspheres made up of carrageenan, and we managed to encapsulate both pure vitamin C and vitamin C extract, but we still need to work on, for example, the encapsulation efficiency and look at the complete release kinetics of the system. What we need to work on also is, like I said, measure the release kinetics. And like was mentioned in the previous talk, this is a sustainable way of using sargassum as a food source, but we also need to look at the safety. And one of our concerns is that sargassum is, even though we did not see any heavy metals in the seawater, species such as sargassum is known to accumulate other heavy elements such as arsenic. And in fact, when we looked at the crude seaweed from around the island, a lot of the sargassum species had pretty high content of arsenic in there, up to 90 ppm of arsenic. And from what I know, the FDA requirement for food is less than 1 ppm. So that's a big concern. So what we are looking at right now is whether when we do the extraction, so look at the extract itself, whether we carry this high amount of arsenic with the extract itself, and or whether it stays in the crude seaweed. So that's something we are working on. So this concludes my presentation, and this work would be very hard to do without the contribution of all the people shown here, especially Dr. Archana Balaximo, who's the director of who's the head of the Center for Biomedical and Biomaterials Research where I work, and all the rest of the team who work on the various parts of the project. So thank you for your attention, and if you have any questions, I'll gladly answer.
Oh, thank you, Dr. Bekah, for that very interesting and also information-packed presentation. I'd like to open up the audience for questions. Yes, please.
Hi, thank you for the wonderful presentation. I just have a really quick question. I'm just curious. So do you anticipate that this method will be more cost effective or will provide added benefits? I'm just curious because right now there are vitamin C supplements. Are you going to be able to market it in a way of how seaweed extracts may potentially have, in addition to vitamin C, maybe other additional benefits? So I'm just kind of curious what your thoughts are.
Yeah, our idea is that we really think about the controlled release of the seaweed extract. So what is on the market right now is just capsules that release everything at once. So what we are really hopeful on is that we can modulate the release of the vitamin over a long period of time. And what we also think of is that in addition to having controlled release, the polymers that we use in the system are all food grade, all organic, if you can say. So even the carrageenan, we are hoping to extract it, to produce it in-house, to extract it from red seaweeds that are available on the island. Same with the chitosan. So everything, that's how we are trying to market it. So.
Okay, thank you. Any other questions from our audience? Yes, I'll come up this way.
Hi, what would be the benefit of a controlled release of vitamin C versus just taking it at once? Thank you.
Okay, so if one of the issues that vitamin C is water soluble. So if you take a large amount at once, or what's going to happen is just you're going to pee it out. It's not going to be very effective. So what we want is you ingest it and then it's released over time, little by little, as you need it. That's why we'd rather a controlled release instead of a burst release of vitamin C. So I'm not sure whether that answers your question.
Yes, that answers your question. Thank you. And one more. If there are no other questions, I'd like to join the audience in thanking Dr. Bekah one more time. Thank you.